Assalamu alaikum. Actually, today we will start with a new playlist. The upcoming playlist will be named Real Function Limits Continuity and differentiability. Today we start by domain of definition. What we call the domain of definition. Let be function, a real function. We say that a given part of R is a domain of definition of any function, defined one, if it makes sense. So, for example, for this function f1, the domain of definition of a1 is equal to all the real numbers from R, such that what? Such that f1 of x has a sense. Can make sense. This is equal to x from R, such that the fourth root of x minus x power 3 makes sense. This means that x minus x power 3 is greater than or equal to 0. And this is equal to. We need to know when for an x from R we have x minus x power 3 is greater than or equal to 0. So we can use the table here, x minus infinity plus infinity. This can be written as x times 1 minus x squared, which is so we develop x minus x power 3. We take x out, then we keep x times 1 minus x squared. Famous identity gives us this. Here 0, so x for it is equal to 0, less than 0 minus and plus than 0 plus. We have 1 minus x, so we are dealing with 1. Here 1 minus x, so this is positive if x is greater than 1 and is negative if x is greater than 1 and positive if x is less than 1. Here we have 1 minus x. And last we have 1 plus x, so we deal with minus 1 and for minus 1 here we have 0, and for minus 1 here we have 0. So plus minus, if x is greater than minus 1 we have plus, and if here plus for sure, and if x is less than minus 1 we have minus. If we take the types, so this function star, we have plus, we have minus, we have plus, and we have minus. So the domain of definition of df1 is equal to minus infinity, minus 1, union, 0, 1. This is the domain of definition of f1. How about f2 of x, which is equal to sometime we can check just to be comfortable. We can take, for example, just to be sure, to be more comfortable, if we take, for example, x equal to minus 2. If equal to minus 2 is negative, 1 minus minus 2, this is positive, and 1 minus 2 is negative, 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 this means it's positive. So, see, just to let you be more comfortable, if we take here, for example, 1/2, 1/2 is positive, 1/2 is positive, and 1/2 is positive, so this is positive. If we take here, for example, this is negative, minus 1/2 is negative, 1 minus 1/2, this is negative, 1 minus minus 1/2, this is positive, and 1 plus x, 1 minus 1/2 is positive. So here we have positive, here positive, and here negative. So this is negative. For this reason, we didn't take this anchor one. For the second one, we have f2 of x is equal to the square root of 1 minus x divided by 1 minus x. The domain of definition of f2 is x from R, such that f2 of x makes sense. So we have here square root. To be well defined, we need two things. We need that 1 minus x divided by 1 plus x be greater than or equal to 0, and we need that 1 plus x is different of 0. This is what we need. The division as the multiplication. Once more, we have here x, we have minus infinity, plus infinity. Remarkable value x equal to -1, -1, this is not allowed, forbidden value, then what we have? We have 1 minus x, this means 1. So 1 minus x. So it is positive when x is less than 1 and negative if x is greater than 1. And we have 1 plus x is negative if and positive if this is positive if 1 plus x. If we take the product, we will get here minus and here plus and here minus if this is the product. So the domain of definition is actually -1 open and 1 closed. You can, for example, take x equal to -2. This will be positive, but here negative. You can, for example, take x equal to 3. This is here positive, but this is negative. This is the domain of definition. Let us move to F3. Let us move to F3, index 3 of x, which is equal to the square root of x plus 2 the square root of x plus 1. As we did last, we have df3. This is x from R, such that this makes sense. This should make sense twice for this square root and the square root, the big square root. So we have two things at the same time, and we have two things to do at the same time. So we solve here a system. So x plus 1 greater than or equal to 0, which is equivalent with x greater than or equal to -1, and second one, and 2 the square root of x plus 1 greater than or equal to -x. Here we have x greater than or equal to -1. This means that x belongs to -1, 0, union 0 plus infinity. We will distinguish the cases for x greater than or equal to -1. If x I will take it here open and here closed. If x belongs to 0 plus infinity, this means that this value is negative or equal to 0. And all positive things, we know that they are greater than or equal all negative things. If x belongs to 0 plus infinity, this is trivially true. So we are interested in the case which is subject for discussion when x belongs to minus 1, 0. When x belongs to minus 1, 0, minus x will be positive. So we can solve this equation using formula. What we can say here, if x belongs to 0 plus infinity, the inequality is true. And if x belongs to minus 1, 0, we have to discuss. So we take off the square root from the both inequality. We get 4x minus 4 greater than or equal to x square. This means that x square minus 4x plus minus 4 less than or equal to 0. So we have to solve this inequality. Delta 22. So the square root of delta is 4 square root of 2. We have two solutions. X1 is equal to 4 minus 4 square root of 2 divided by 2. This means 2 minus 2 the square root of 2. And x2 is equal to 2 plus 2 the square root of 2. So this is true. We are working just in minus 1, 0. So this formula is true if x, we have the domain x1, x2 is positive, 2 plus 2 square root of, but we are working just for 0. We are just working here. Between the solution, it is negative, and out of the solution it is both positive. So the domain which solves this inequality is just this one. It's just this one here negative and here positive. But we are interested just between minus 1 and 0. But 2 minus 2 the square root of 2 is somewhere here minus 1 is somewhere here. So the domain of definition is from x1 up to plus infinity. Then we can write here the domain of definition is equal to 2 minus 2 the square root of plus infinity. This is the domain of definition. So we have to discuss cases and take up the adequate cases of solution. For F4, actually we have to do the same thing like here, dF4. I think that it will be equal to 1 plus infinity, 1 plus infinity. Do it or check it. For F4, F5, ln x minus ln x. We can write this ln x minus 3 divided by x to find the domain of definition, this is not true. You have not to do this. Find the domain definition without making any simplification, any change on your original functions. We have to give the domain of definition of this function without making this transformation, which is true. So do not do this. Domain of definition of phi is x from R such that it makes sense. This means that x minus 3 is greater than 0 and x greater than, strictly greater than 0 to define the ln. This means that x greater than 3, which means 3 plus infinity. How about f6? Domain of f6, is x in R such that this makes a sense, which means 1 plus the integer part of x is strictly greater than 1. The integer of 1 plus the integer of x is strictly greater than 1 means that the integer of x is strictly greater than minus 1. This means that the integer part of x is equal, greater than or equal to 0. This means that we start from 0, which is equal to 0 plus infinity. How about f7? f7 of x is equal to logarithm of the logarithm of x. So the domain of definition of 7 is x such that ln x is greater than 0. This means that x such that ln x is greater than 0. This means that x such that x is strictly greater than 1. So we start from 1 to plus infinity. We can do the same thing with ln 1 minus 3 divided by x, so it will x minus 3 divided by x. We make the table as x minus 3 positive negative, x positive negatives. We take the times because it is actually as if we divide it. Then we can find the domain of definition. Here we need ln x minus 1, so it makes sense if ln x minus 1 is strictly greater than 1. This means that x strictly greater than 0. This means that x minus 1 is greater, ln x minus 1 is strictly greater than 0. This means that ln x minus 1 is strictly greater than 1, and so on. We can do it. F9, for example, or actually it is easy. It is easy. You have just to be careful to define the good value of ln x. The F9, this is x from R, such that what? Such that ln x minus 1 is greater than 0 to be well defined. This means that x from R, ln x minus 1 greater than 0. This means that x minus 1 is greater than 1. This means x greater than 2, and the domain of definition becomes 2 plus infinity. I told you it is easy. Time, I need to check the time. 24 minutes. So I will let F10, F11, F12 and F13 to the next video, part 2. Thank you very much. See you next time.